Hello and welcome to Learn Data. It's great to have you on this channel. In this video, we'll continue our discussion on Gaussian mixture models. Moving on to part 2, let's look at what is expectation maximization. And because this is a method used in one of the methods available in Scikit-learn to perform clustering. So expectation is something like weighted averages. So for discrete and continuous distribution, so here we have a discrete distribution. So this could be count of uh, number of apples on a tree, and we have 1, 2, 3, 4, and in the bottom we have continuous distribution. So the numbers are continuous, so this could be height of people. So to calculate the expected value, we are multiplying each of these readings on the x-axis by the corresponding probability values and summing them up. So that's what we see here. And for continuous distribution, we are taking an integral. Here is an example in the discrete case where we have these values. So based on the formula, what we would do is multiply 0.2 with 1, then add it with 0.3, multiplied by 2, and so on, and we get a value of 2.4. If you manually calculate this, the weighted mean, it would be something like this. So you can convert 0.2 to 2 by 10, 3 by 10, 4 by 10, 1 by 10, and then uh, add the proportions, and in the output you get 2.4. Now let's look at this plot where we can see how expectation maximization could be used. We have two sets of data points, one on the left, and we have a second set on the right hand side, shown by these circles. And we have two features, one on x-axis and the other one on y-axis. And the way we can begin is by random initialization of by data points shown here by the plus signs, red plus signs. Now, the very first step, then a general approach is that what we do is we find the distance of all the data points to each of these um, as random initialized seed data points. And based on that, we can decide which points are closer to each of these and which points are farther. And accordingly, we can move these plus signs towards those groups and to get the final position of the centers to identify the clusters. So we have these, and then each of these could be representing distribution. So here I'm showing a perfect uh, circle, so which means that there is no correlation between the x and y features for these data point, and same thing here. So for expectation maximization, what we are trying to do is we are trying to find a Gaussian distribution that best represents the group of clusters we are looking at. So we get the maximum value for maximum expected value. And so to get there, because these points are farther away from these groups, the values would be lower. But then as we move closer to these clusters, the value would increase, and finally when we reach when the solution converges, that is to say when the value for the when the expected value kind of reaches the maximum, does not increase further, we know that we have reached the we have found the clusters. So that's where we can then represent a Gaussian distribution to we can use a Gaussian distribution to represent that cluster where as shown here. So we have one cluster here on the left hand side, we have the second cluster right here on the right hand side. We started with these data points shown here, and then we finally arrived at these locations which are shown here by the green colored X. And as we can see, these are contour plots. So in which means that this would be a two-dimensional surface plot if we looked at it in a 3D plot, and each of these lines represents the probability density. So what this tells us is that this how likely this point is that it came from this distribution, and similarly for all the other data points. And another point to note here is that these uh, the shape of these contours is oval, and that tells us that there is some relation between this feature 1 and feature 2 in this case. Next, let's look at the terminologies that will come across when looking at the expectation maximization algorithm. And the terminology is KL divergence and lower bound. So in expectation maximization, what we are trying to do is maximize the likelihood function that P of x given theta. So theta here are the parameters, and so that is given by the joint distribution sum over the joint distribution for x and z given theta. So z here is a hidden variable or the latent variable that could represent the number of clusters, and theta parameter could represent the standard deviation or the variance and the mean of each of those clusters. So in order to solve this particular equation, the likelihood equation, so what we would do then is we would use the priors for the parameter theta, and then multiply the likelihood with the priors to update our priors to that is to say we calculate the posterior. The posterior is nothing but the updated priors after we see the data, which is given here by the likelihood. So in that particular situation, what happens is we have the denominator in the base formula, which is the evidence, that becomes difficult to calculate, and so an alternative is to perform this decomposition of that equation. We are not going through the derivation here, but just to show you what the final output of that derivation would be. So we have the log likelihood that is equal to the lower bound of q and theta plus the KL divergence of q and p. So this term right here, it represents the difference between how far apart the distribution q is from the distribution p. And here on the lower bound, this is the log likelihood of the function log p of x given theta. And so that is given by these two relations shown here. And here q again, q and p is we are trying to find the difference between these two. Now these plots would help understand how that works. So let's say we have two discrete distributions, p of x and q of x as shown here, and we have these four four ticks shown here, and each of all of them add up to 1. So we have 0.25. Now if you look at both of these, the Keil divergence between these two would be close to 0, and so that is to say the Keil divergence is small, and therefore those two distributions are similar. So when we go back here, uh, we could say that the solution has converged. And on the other hand, if we see a difference, a large difference between the two distributions, then the Keil divergence is large, and so we'll continue to iterate through the optimization process. So here what we are trying to do, we are trying to maximize the lower bound. What that does is it um, reduces the Keil divergence, and that in turn maximizes the log likelihood. And here, let's now move on to the intuition of k-means, and also we'll look at the Gaussian mixtures. So we have these set of data points shown here in gray, and we can see that there could be this cluster at the bottom, and then there is another cluster at the top right there. We initialize with two data points. These could be random initializations anywhere in the space, or they could be uh, any two data points from the data set that we have. And this is a very important first step, because if the initializations are not optimal, thus the output could be uh, totally different than what you would expect. So initialization is important. So what we can do is, let's say if we initialize these 2 points, then the first step would be to find out the distances between each of these points to the seed points, and based on their distance we can find out if this point is closer to the red x or the blue x. So for example, this is closer to x, so we will make that red. This is closer to this blue x, so we make that blue, and so on for other points. And thus we can draw a perpendicular bisector from between these two seed points, such that which tells us that the points on the left would be blue, points on the right would be red. Now after this step is done, the next step would be to find out the new uh, location for these x's based on the colored points that we have created. So let's say these points move in this direction. So once that is done, then we begin from the start. Again, we can draw a perpendicular bisector, or we can find the distance of each of these points from the x's, and then based on how which uh, x each of these circles are closest, we can assign them to that group. So these become red, these become blue, and so finally we would have found the clusters, which would be these clusters. And in this case, k means there is an assumption that both the clusters have equal variances. And another point to note with k-means is that the decision boundaries are linear, as shown here by the straight line. And this can be sometimes useful and sometimes not. As we'll see in case of Gaussian mixture models, as shown here, we have similar set of data points. Let's say we initialize on the two x's right here, and now find the um, we find the likelihood that a point would belong to a Gaussian distribution, which is represented by the mean and variance or covariance of a distribution located at this point or this point. Essentially, that comes down to finding the distance, square distance from these x's or the seed points that we have. The point to note here, which is different than k-means, is that when the points lie on top of the decision boundary, in k-means we would have assigned this point to completely to a red cluster and this point maybe to a blue cluster based on a certain criteria. Uh, let's say if the probability for this point to lie on the red side is 0.75 and it's higher than 0.25 probability to lie on the blue cluster side, so we can assign that point to the red cluster. So what that is called is as hard clustering. There is no middle ground. It's either yes or no. And in case of Gaussian mixture models, there is something called as soft clustering. So here, for example, these three data points shown here in the gray are enlarged here on the right hand side, and we can see that 75% 75% of that data point lies in the red region and 25% lies in the blue region, and so on for the other data points. So these data points are classified based on the proportions they are. So they belong to both of these classes, and to the extent to which or the proportion to which they belong to each of those classes is determined by these values that are shown here. And again, so with that in mind, we continue. The rest of the process is same. So we continue with finding the data points and then again shifting the seed data point that we started with, and thus we arrive at this final location where we have identified the clusters. And so identified the clusters in the sense we have identified the Gaussians that represent those cluster of data points. And here in Gaussian mixture models, the decision boundary can be nonlinear, and which could help uh, find clusters in more complicated structures of data sets. So here is a mathematical for notation for the Gaussian distribution. The top one is for univariate case, so by which I mean we have a single variable x. I have the mean for that. Sigma is the standard deviation, sigma square is variance, and this is the formula for that. And then for the multivariate case, we have the same thing except that we now have vectors and matrices. So x is represented by a vector of variables. So you have vector mean vector again, and then we have the covariance matrix of size d by d. So that d is coming from the length of the x vector, and the rest of this is the can be derived from that. And here is another illustration of how the Gaussian mixture model would look like. So here, let's say we just have one feature, and we have a data set that looks like what we see on the left hand side. And within this curve, we can tell that there could be two Gaussians that have that together show this outline that we see. So the task of the clustering algorithm is then to find out this group of data points or this Gaussian from this Gaussian, so that in after the model is fit clusters are found, we can identify those two separate clusters as shown here by these dotted lines. So again, with soft clustering, what we have is data points that are that may be right here that belong to both of these clusters would be represented by the proportion to which they belong to each of those clusters. And here is an example with more number of data points, and this could be called as bivariate because we have two features. And as we can see, the algorithm is able to nicely identify these two separate clusters, each of them represented, the centroid is represented right here in the center. So what this is telling us is that let's say based on the values of the probability, that these data points are more likely to have come from the Gaussian distribution that is represented by uh, these contours shown here at the bottom, and then same thing goes for the distribution for the orange data points shown up top. That was it for this video. We'll continue the discussion on Gaussian mixture models in part 3. Please like, share and subscribe. Thank you.